Hello, and welcome to this GIS tech video on basic spatial analysis with geographic information systems. The learning objectives for this lecture are to describe what spatial analysis is, describe select basic vector-based geoprocessing operations for spatial analysis, describe select basic raster-based spatial analysis operations, and compare and contrast various basic spatial analysis methods in industry standard GIS tools through hands-on demonstration. A dictionary definition of spatial analysis is that it is the process of examining the locations, attributes, and relationships of features in spatial data through overlay and other analytical techniques in order to address a question or gain useful knowledge. Spatial analysis extracts or creates new information from spatial data. Spatial analysis is a core process supported by GIS software that makes GIS software unique from other analytical tools, given the emphasis of examining spatial data and relationships. Additionally, spatial analysis is the driving force behind many GIS software functions. In the next part of this lecture, I will discuss select examples of different spatial analysis tools. Spatial analysis tools are often specific to the underlying data model of the data being analyzed. With vector-based points, lines, and polygons, there are several what are known as geoprocessing operations. Many of the vector geoprocessing operations function as input-output operations. This means that an input feature like a point, line, or polygon is used to create a new output feature that is created based on the geoprocessing operation. In the next part of this lecture, I'll give you some examples of commonly used vector geoprocessing operations. Buffer. Buffer is when an input feature is used to create new output features at a certain distance around the input feature. For example, if we have a point as an input feature, we can then tell the buffer geoprocessing operation to give us an area that is 500 meters around the input feature. The buffer geoprocessing operator will then create around the input feature a new output feature that is 500 meters around the input feature. Clip. Clip is when a feature called the clip feature is used to extract an area from an input feature to create an output feature. One way to think of clip is like making cookies. You can think of the clip feature as the cookie cutter and the input feature as the dough from which the cookie is created. For example, if you have an input feature, you can then define a clip feature for the area you want to clip out from the input feature. The output feature is then clipped out from the input based on the clip feature used. Dissolve. Dissolve is when features are aggregated based on a common attribute. For example, this image shows census tracts by county as indicated by the different colors. Dissolve can be used to aggregate the census tracts by county. When the dissolve operation, using counties as the dissolve attribute, is run, the output features show how census tracts have been combined or dissolved based on their common attributes. Union. Union is a function that computes the geometric union of polygon features. For example, in this image, you see three features: two blue rectangles and a yellow circle. When the union geoprocessing operation is run, a total of 5 new output features will be created based on where geometric unions between the 3 original input features were found. Identity. Identity is where the geometric intersection of the input features and identity features are computed, and portions of input features that overlap identity features will receive attributes of the identity feature. For example, let's say you have 2 input features. They have an attribute of A for feature 1 and an attribute of B for feature 2. The identity feature has an attribute of C. After the identity geoprocessing operation is run, 4 output features will be created. Features created where the identity features touch the input features will have attributes of both the input feature and identity feature. Intersect. Intersect is where the geometric intersection of input and intersection features is computed. For example, given a set of input features and an intersect feature, after the intersection geoprocessing operation is run, the output feature will only have the area where the inputs were intersecting with each other. In the next part of this lesson, I will discuss select examples of raster-based spatial analysis methods. Raster spatial analysis works on doing calculations of raster grid cell values. One way to begin understanding raster-based spatial analysis is map algebra. Map algebra is the idea of doing various mathematical operations on raster cells to create a new output raster. For example, let's say you have 2 raster data files. In this example, colors in each cell represent the same cell in each raster in terms of spatial extent. For example, the blue cell at the top of raster 1 is the same cell in terms of spatial extent as the blue cell in the top of raster 2. Using simple map algebra, the 2 rasters can be added together on a cell-by-cell basis. This in turn creates a new output raster that has the combined values of the 2 input rasters. Another example of map algebra is multiplying raster cells by a constant value. For example, many digital elevation models, or DEMs, contain topographic cell values that are in metric, like seen in this hypothetical example. Given that there are 3.28 feet to a meter, each cell value can be multiplied by a constant value of 3.28 to create a new output raster that contains the cell values based on the multiplication of the input raster by the constant, and in this example, creating a new raster grid with feet-based cell values instead of metric values. In the following slides, I'll give you a few more examples of common raster analysis methods. Slope. Slope is the idea of calculating the maximum change rate between a cell and its neighbors. For example, here we see a digital elevation model of a mountainous area. After the slope tool runs, an output is created indicating the degree of change between cells. Slope is commonly used with elevation datasets and in site selection problems where it is necessary to determine flat areas. Hillshade. Hillshade is where the sun's relative position is taken into account to create an output grayscale representation surface. You can think of the hillshade like shining a light over a topographic surface. The altitude and azimuth, or compass angle, of the light source will determine how the shadowing in the hillshade surface is created. For example, using the previous elevation surface, we can run the hillshade command to create the output hillshade. In this example, the default azimuth of 315 degrees, along with an altitude of 45 degrees from the horizon, was used as the light source, thus creating the darker areas under some of the mountainous peaks as seen here due to shadowing. Euclidean distance. Euclidean distance describes each raster cell's relationship to a source or set of sources based on the straight line or Euclidean distance. For example, let's say you need to know the distance between hospitals for planning a disaster evacuation. This figure shows examples of source cells, which in this example are locations of hospitals. After Euclidean distance is run, an output raster is created that shows distances between the source cells, or in this case, hospitals. Such information could be helpful for planning distance between evacuation activities as to which hospitals injured people should be sent to. In the next part of this lesson, I'll give you a hands-on demonstration of some of the techniques previously discussed. In this hands-on demonstration, I'll give you an example of using some of the vector-based geoprocessing tools you learned about for a hypothetical spatial analysis. Specifically, I will do an archaeological sensitivity spatial analysis. The analysis will be to see what areas inside a 500-foot buffer of a proposed interstate reroute are archaeologically sensitive. For example, are there any Native American or historical structures that should be accounted for before construction of the interstate begins? To facilitate our spatial analysis, we will use a simple model to develop a final area archaeological sensitivity score. Specifically, we will calculate distances from historical structures times distance from water to derive an archaeological sensitivity score. The following image also helps illustrate this idea in terms of the final output from the spatial analysis. This image shows an example of the study area. The red line indicates where the proposed interstate reroute is being planned. This is in relation to the existing interstate that is to the east or right of the reroute. This dotted line represents the 500-foot buffer around the proposed interstate reroute that is of interest for the archaeological sensitivity analysis. Finally, these polygons represent areas determined to be of archaeological sensitivity based on the spatial analysis and modeling conducted using the parameters discussed in the previous slide. In this hands-on demo, I'll show you how to do such a spatial analysis and model. I'll also show you how to create a basic elevation effect using some of the raster techniques previously discussed. In this hands-on demonstration, we'll do an archaeological site sensitivity model using some basic vector geoprocessing operations. Now, one important thing to keep in mind when you're doing geoprocessing is the input-output factor of those operations. So one of the first things you want to do when creating a new map document is actually create a default geodatabase. So let's go over that first. So I have an unsaved map document here, and I'm going to save it near my data sets I have set up for this. So by doing that, you can see over here in our catalog, my map document is next to some of my data sets I'll use for this demo. But an important thing I want to do here is go File, Map Document Properties, and you can see here where it says Default Geodatabase. Because of all the input and output we're going to be doing, we want to know exactly where our outputs are going. And the system default geodatabase is okay, but if you're planning to move your data around off of different computers, it's really helpful to have your own default geodatabase. So I'm going to click here, and I'm going to go in my home directory, and I'm going to click right here where it says New File Geodatabase. And I'm going to rename it and call it Output. And it's a little tricky with the clicks here, but rename it, click off, and click back on it again. And you can see it changes it here. And I'm also going to store relative path names that'll make sure that all of my data stays relative to my MXD in case I need to move it. So we've got that set up. Now, the very first thing I want to do is bring in some of these data sets. So back to our original discussion about what this model and analysis will be, we're going to look at archaeological sensitivity to a proposed interstate reroute. So I'll bring over that reroute data, and it's going to be a simple line feature. And I'll just ignore that, and we'll make that maybe a little more clear color, make it stick out good. So this is the area that we're going to be interested in 500 feet around in terms of archaeological sensitivity. Now, I also have some historic data to give some context. For example, I can bring in, here we see a historic map of my study area from the 19th century. And I had previously digitized some of the buildings off of this map. So I'll bring those in. And I'll make those stick out a little better too. Maybe I'll make them red, a little bigger, so we can see what's going on. So if we zoom in a little closer, we can see how there could be some areas. Here's the proposed reroute, the red line, and structures near that reroute that have been digitized off a historic map. Now we're also going to bring in water. As per the original model, we're interested in distance from, I should say, buildings and from water. So I'll bring a water layer in, and I'll make that a little clearer to see as well. Make that blue for water, and so forth. So here's the spatial relationships we're interested in. We have the proposed reroute in red, water, and structures shown as dots. Now to set things up as well, I'm going to actually add a new field to the structures to give those structures a point value for calculation with other outputs, and that'll become more apparent as I move through this. But what I'm going to do is I'm going to go to the attribute table of structures, and I'm going to click add field, and I'm going to call it struct val for structure value. I'll keep it a short integer, and I'll hit OK. And you can see those are all null. And then I'm going to use the field calculator, and I'm just going to give them a number 10. And that's a very arbitrary choice. You could make that any number you want. When you see the final output of this, it'll probably make more sense why I'm doing it with 10, but it really can be any number, and that's a much bigger topic in terms of spatial modeling and weights and so forth. But I'm just going to go ahead, use field calculator. So now every structure has this arbitrary sort of weight of 10 given to it. Okay, so now let me show you how buffer works. The first thing we want to do is create a 500-foot buffer around the interstate reroute. I'll turn a few layers off to make this more apparent. We'll zoom to that layer. And for your own training, there's several ways you can actually go about running the geoprocessing tools. In newer versions of ArcMap, they now have this handy menu right here with some of the more common ones that you saw in the earlier parts of the video. But just for thoroughness of the training, you also have a search tool where you can type the name of the tool in that you want. In this case, we want buffer analysis. You also have Arc Toolbox that if you get really good with ArcMap, you can hunt around through here and go analysis tools, proximity buffer. So I find that there's so many tools, I often just use the search tool, but you can get to it as well through Arc Toolbox or through the geoprocessing menu up here. But in this case, we're just going to use the tool, we're going to access it here. And in this case, real straightforward here to use a lot of these tools, input and output like you learned about earlier. We're going to pick proposed 390 reroute. And notice here now the output feature class by default is going to that output geodatabase we created in the beginning. So I'll just leave that default, and you can see that it's going to give me a name, the name of what I'm buffering plus underscore buffer. And in this case, we want 500 feet, so I'll change that here. And we'll just leave all the defaults and so forth. So with that all set up, I'll move this over so you can see. I'll close a few things too. We'll hit OK, we'll watch it run. Like any kind of tool, make sure you look down on the bottom right to see the tool running. And there comes our very first buffer as part of this modeling task. We zoom in a little closer, you can see the output and so forth. And it's automatically added to our map. Now we're going to save it. Okay. Now you can actually do buffers, multiple ring buffers at multiple distances. And in this case, we're going to have our water sensitivity be factored by multiple distances from water. So again, I'll turn that layer back on. And if we zoom out a little bit, just look at those spatial relationships. So forth. So now let's do buffer again, this time a multi-ring buffer for the water layer. So in this case, we actually have to use a slightly different tool to create a multi-ring buffer, and I'm going to get to that by going back to the search tool, and I'm going to type in multi-ring buffer. As you can see, there's a slightly different tool, but again, that search box can be very handy for finding what exactly it is you need. So I'll open this up, and you can see now it has a similar kind of interface, but slightly different parameters you put in. So in this case, I'm going to do Livingston Hydro subset. Again, here we see that default geodatabase, live hydro subset, multi-ring, and the first distance I want is going to be 250 feet, and the next distance is going to be 500 feet. And I use the plus sign to add that. So input is the live hydro subset water, output is going to be sent to my default geodatabase, and I'm going to get two buffers created based on these distances I've inputted in the list. And you can see you could have a lot more. I'll leave all the other defaults as need be, and I'll run this tool. And like always, I look down here to make sure my output is happening okay. And we can see here that the multi-ring buffer ran correctly. So I'll make the screen a little more visible here. Now, this is a good example too of how things can quickly start getting visually cluttered and a lot going on here, but it looks kind of interesting. So to kind of summarize where we're at, we just ran a multi-ring buffer of the water sources at 500 and 250 feet, and we're now going to start looking at the relationship of those with a reroute buffer of a road. And the next thing we need to do now is do a buffer of distance from structures. And in this case, we're going to do a 1,000 foot buffer around the structures. Now, again, that's a very arbitrary number I picked, and that's sort of the challenge of doing modeling, is how you determine distances and how you determine weights and so forth. But since this is more focused on just showing what the tools can do, we're not going to worry about that too much. And we'll go ahead and do a buffer of the structures. So again, I'll use it by getting up here. Now, in the previous examples of buffers, I haven't really changed any of the other parameters, but in this case I am going to change, and I'll show you what I'm going to do. So in this case, I'm going to select structures as the input. Again, my default geodatabase is set up to receive my output. I'm going to set it to 1,000 feet. And if you look at some of these other parameters down here, one of them is dissolve type. And so far, we've been selecting, we've been dissolving things, but in this case, we're going to leave it as none. And that means that every one of those little red dots is going to have its own individual buffer circle around it. And that's different than what we saw with the stream buffer, where there was basically one buffer feature created per feature. So in this case, I'll hit OK. Watch this run. As always, we're looking down here. And you can see in this case now, zoom in a little closer on what we have. Like I said, every one of those red circles, every one of those red dots created its own individual buffer circle. And if we look at the attribute table, you can see that we have a lot of buffers. 182 got created, and so forth. And you can see too in the output that the structure value came along, and we're going to see what that does for us in just a moment. Okay, so the next thing we're going to do now is we're interested in unioning the structures buffer with the multi-ring buffer of the water. So we take a closer look just at those two. And so forth. There's the proposed reroute in red. Here we can see lots of spatial overlaps between distance from the streams, shown in blue, and distance from structures. And we're interested now in terms of spatial analysis in seeing sort of combinations of these areas based on scoring. And what I'm going to do for that now is use the union. So what I'm interested in doing is combining the multi-ring buffer of water with the buffer of the structures, and by doing that union, it'll also combine their attributes together. So again, it's very handy for this particular one. I'm going to go to Geoprocessing Union. And you can see here, like you saw with the multi-ring buffer, I have a list of features I can add to the Union tool. So in this case, I'm going to do the multi-ring buffer of hydro or water, and then also the structures buffer. I'm going to put those together, and I've got a little warning. That's not a big problem. Yellow means you can still go. I'm not going to worry about it. Again, here's my default geodatabase, all set to receive that. We're going to join all the attributes, and we're going to let this run. Okay. Now we have that warning about the data, but we're not too worried about that. Now we can see things are getting really sort of visually interesting here. So now this is our union of the two buffers, and you can see it's very messy sort of looking, but it's actually a good thing because attributes from the two buffers are now part of this output buffer. And if we look at the attribute table here, when you see a struct val of 0, that means a spot where the water buffer did not touch a structure, whereas when you see a struct val of 10, that means there was a structure there, but if it's over here means with 0 means there was no water, and so forth. So what we're going to do now is we're going to basically do multiplication between this field and this field to look for cases where there was an overlap. So for example, a distance of 250 times 10 or a distance of 500 times 10 and so forth. And that should give us 3 output categories because anything multiplying by 0 will come out as 0. So to do that, I'm going to create a new field called score. I'll make it a short integer. And I'm going to right click on that new field and use our field calculator again. In this case, score is going to be equal to the distance, which was the attribute that came in from the multi-ring string buffer as part of the union, times the structure value, and that's it. So a simple multiplication of those two fields to give me a score value, and I'll hit OK. And you can see here, now I've got values of 0, 2,500, or 5,000, 3 categories. Okay. From that, I can do a quick symbolization. If I go to the properties, and you can start to see now anything in green was 0, anything in sort of this purple color was 2,500, and anything in 5,000 is the pink color. And so I'm going to save my work. And now, as you can see, this is very cluttered and messy, and this seems like a really good job now for the dissolve tool, because at this point I have either no sensitivity, medium sensitivity, or high sensitivity. So again, I'll use from this handy menu here, geoprocessing dissolve, and my input's going to be this one right here, that from my union, and I'm going to call this one, I'll call it the final because we're getting close to the end here. And with the dissolve, I'm now going to dissolve. As you remember, dissolve is based on common attributes, in this case score. There's only 3 unique score values, 0, 2,500, or 5,000. I'll leave all the defaults. I'll hit OK. And you can see here, dissolve cleans it up a little bit by comparison to what was underneath it. And I can turn that one off. Now if I go look at the attribute table here, you can see we've got just basically, it dissolved everything down into 3, either 0, 2,500, or 5,000. And again, I can symbolize this to make it a little more intuitive. Based on categories, unique values. I'll add those all in there, maybe use a different color ramp this time to make it a little easier to read. Uncheck that. And here you can see our output. So again, zeros. Now we could even, in terms of symbology, if you're not interested in those not sensitive areas, and so forth. Okay, now finally, to pare this down, if we go back to the original goal of this analysis, we're interested in sensitive areas that are within 500-foot buffer of the proposed interstate reroute. I'll change the symbology of that buffer. I'll make it red, a little thicker. As you saw in the graphic, I can also maybe make it a different kind of line type, like one of the, say, dashed lines. It's really up to you, whatever you think is best, but I'll do something like that. So we're basically interested in just these areas from the dashed line inside the buffer. And this is a good example now of where we can use the clip tool. So basically, the clip feature is going to be the buffer, the proposed 390 reroute buffer, and we're going to clip out areas from that final that are sensitive. So to use this tool, again, we go to Geoprocessing Clip. The input features are going to be the final layer. The clip feature is going to be the proposed 390 reroute buffer. Once again, we have it all going into our default geodatabase. We'll ignore the optional parameters. We'll hit OK. And here we now have the final clip. And there's our final product from this analysis. So if you can see now that it clipped it out just inside that buffer. Again, we can do the symbology on it. We can change the labels around. Perhaps we can move this one out. To get a sense of things. And if we look at that now in relation to, say, some of the historic data that we used originally, you can see kind of where things came from, like some of these structures down here and so forth. Now, last thing I want to show you real quick is how you can go about maybe creating a background for this with some raster data. I do have a digital elevation model of this study area, and we'll bring that in. And you can see that this digital elevation model is relevant to maybe this part of the study area. You might do this to create some context and so forth if you're not happy with some of the other default options that ArcMap gives you and so forth. So to do that, we're going to what we'll first do with our DEM is we'll change its symbolization. And we'll use an elevation ramp like you saw some of the graphics I used earlier in the video, something like that. Okay. And we'll turn that final clip off just for demonstration. Now, again, if you don't know where to find the tools, you can use search. We're going to use the Hillshade tool, and you do need the Spatial Analyst extension. So to make sure you have the Spatial Analyst extension, you go to Customize, Extensions, Spatial Analyst. If the extension's not turned on, make sure you check that box there. Hit close. And then, again, I'll use the search tool to find it. It's called Hillshade. And we want Hillshade Spatial Analyst. And again, it's a very easy to use tool. It's an input-output. The input raster in this case will be the DEM. The output here again, once again, we see our default geodatabase. I'll leave the azimuth and altitude values by their defaults. I'll hit OK. And you can see we get the hillshade gets created behind us here. And now you can do an interesting basic visual effect by taking the DEM, putting it on top of the hillshade, going back to the DEM, go to its properties, and change its display, its transparency to say 50%, and that will make the colors transparent to kind of reveal the hillshade behind it with a coloring pattern. And you can see we kind of get a neat effect with that with looking at like a stream and so forth, so that if you were then go build your final map product from your analysis and so forth, you can add a little more context to things. So also should note, again, that default geodatabase, here's all those outputs were created in one nice spot. That's why it's important to keep everything all together. So I hope you enjoyed this demonstration, and again, like I said earlier in the video, keep these ideas in mind around spatial modeling in terms of weights, parameters, and so forth. There's much, much more that can be done with these techniques. In this lecture, you learned how to describe what spatial analysis is, and that spatial analysis is a core process supported by GIS software that makes GIS software unique from other analytical tools, given the emphasis of examining spatial data and relationships. You also learned how to describe basic vector geoprocessing operations for spatial analysis, such as buffer, clip, dissolve, union, identity, and intersect. Keep in mind, too, that these were just a selection of the most common vector-based geoprocessing operations. You should further explore geoprocessing capabilities of your GIS software to see what other geoprocessing spatial analysis options exist for you. You also learned how to describe basic raster-based spatial analysis operations, such as basic map algebra, slope, hillshade, and Euclidean distance. Like the vector tools, I only showed you a small example of the many raster-based spatial analysis tools that exist. And you should conduct your own further research to find raster-based spatial analysis tools that match your spatial analysis needs. Finally, I showed you how to compare and contrast various basic spatial analysis methods in an industry-standard GIS tool through hands-on demonstration using an example of archaeological site sensitivity modeling. Spatial analysis and modeling is perhaps one of the most powerful aspects of GIS in terms of decision-making and spatial insight. I strongly encourage you to use the ideas from this lecture as a starting point for your own spatial analysis. The following are references used in preparing this lecture. If you enjoyed this GIS tech video or have any comments or questions, feel free to contact me at the email address below. Thank you for watching.